Residence time is the length of time that a substance persists in a system. So the system that we have been going through this semester is a hydrologic cycle. So water can be in one of the reservoirs or in flux a certain amount of time. But we also use residence time to talk about pollution in one of these reservoirs in the hydrologic cycle. Basically, how long will a spill or pollutant stay in that reservoir? Rivers, it's something like 2 weeks, and that's going to depend on sedimentation. Does the pollutant settle out quickly and become part of the channel sediment, or does it wash downstream? If it continues to move downstream, it looks like 2 weeks, but if it gets trapped in sediments, then it could stay there essentially forever. Lakes are about 50 years, groundwater 100 to 1,000 years before the pollutant gets out of the system. Glaciers are a different story. We don't usually pollute those, but the water stays in there, maybe even 1,000,000 years or so. Think about measure quality. I've already talked about the term TDS, that's total dissolved solids, but let's go back and we can look at individual pollutants and we can talk about those in terms of ppm. So if there's a chemical substance that is in water supply, we may say it is ppm, parts per million, or ppb, parts per billion. So an example would be if water contains 1 parts per million of salt, it contains 1 gram of salt per million grams of water. Sorry about that. Or we can look at it as a whole, like the total of the dissolved solids. So that's the term TDS. So we may say that there's 500 parts per million total dissolved solids, and that would include everything, not just salt. We can also measure electrical conductivity. There's a meter for that, and the meter has 2 probes on the end of it, and the measure would be to see if there are ions in the water. Electricity is the movement of these electrons, right? And so if the ions can move those electrons, then they can make electricity. So the probe is basically trying to see if an electrical current can go through the water and how well it can. That's a measure of the amount of ions in the water, electrical conductivity. Another one is pH. pH is the negative log of the concentration of hydrogen in a substance, a liquid usually. So you like to say it's a measure of acidity or alkalinity. Is it acidic or is it basic? That hydrogen in there is, if there's an elevated amount of hydrogen, then it's more reactive. And so that means it's a more acidic solution. Okay. It's a negative log of that concentration. So the lower the pH, the more acidic. Neutral is 7, and a higher pH then is alkaline, and that is a more basic solution. So the acids, oftentimes it's from acid rain, or from industry, or from acid mine drainage. Another measure we make is whether or not water is hard or soft. Hard water is produced when groundwater flows through carbonate rocks. Hard water occurs when water flows through carbonate rocks, whether it be a limestone or a marble or a dolostone, and it picks up calcium, making it hard water. If it picks up that calcium, it makes it so that soap doesn't lather very well. Bathtubs are going to get rings around them. Clothes might turn gray. It's just an added ion in there that makes the water calcium rich. That calcium can build up in pipes, coffee pots, steam irons. Those can get gunked up by that calcium deposition. The water can be softened with a softener, so that would be in line in your water system at your house. And usually, though, that softener is a sodium chloride mixture, which is a salt. And it's not good for you if you're on a salt-restricted diet, but you can fix, quote, hard water. We've been kind of focusing on surface water here, but groundwater can also become contaminated. through weathering of rocks, petroleum, landfills, human waste, agriculture, gas stations, polluted surface water. There is a direct connection between the surface and the groundwater. Dry cleaners. Dry cleaning is actually pretty nasty chemicals that can get into our groundwater supply. Your houses can, whether it's through a septic tank or whatnot, or just some people would just dump chemicals in their backyard. There's natural contaminants like those radioactive ones. So groundwater can be polluted just as easily as surface water. And here's a look at all the different ways we can pollute the groundwater. We've got an unlined landfill, so that leachate is going to allow for the infiltration of leachate down into the ground. Old tanks. People don't even know sometimes they have an old tank leaking in their yard. Septic tanks leaking, agricultural runoff getting into the surface water that can then infiltrate into the groundwater. Here's leaky injection wells. Injection wells are where we are disposing of hazardous chemicals. So all of those different ways we can start to pollute the groundwater. The groundwater, we're going to talk about that a little later in the semester, that chapter. Then it's hard to clean up because groundwater is on the move. Here is a house with drinking water well and contaminated or groundwater flow intersecting that septic tank, and that's a good setup right there. If that flows down though to the next house, maybe the next house though is going to get polluted water from that septic tank. So you've got to really be aware of which way the groundwater is flowing, because you can have the contaminated plume coming off a septic tank. How do we remediate that? How do we clean that up? Well, we've got to really constrain the parameters here. You have to map out this is a map of the groundwater flow across these elevation lines of the water table. We have to contour out the plume. We call the pollutant a plume. And then it gets expensive. Look at this. Here's a treatment plant. So they would actually have to put in infrastructure to capture that pollutant. Here they're trying to intersect the movement of that pollutant from this factory, and then they would suck that water up and treat it and then put it back into the ground. So these become really expensive processes to try to clean up groundwater.